Hello, everybody. Apologies for that. There was a glitch in the matrix, but we are back. I hope you're doing well. And welcome to this latest episode of the Ask Abhijit show. This is episode 199. We are just one episode away from the double century mark. So, thank you so much, all of you, for being part of this wonderful adventure. And thank you thank you to all of you who are on the live chat live stream right now. Let me see who all is there. Today is the science episode. We're going to talk about science. I'm going to take questions from the comments, and I'm going to answer the best of the questions that you've asked. So let me see who all is there on the live chat. I can say Suhas Reddy, Parasatav, uh, Kenneth Tan from the Philippines. Hello, nice to see you, sir. Dungar Singh Chauhan, great to see you. Vaibhav, Anvit, Akash Pandey, Abhishek Srivastav, Begum, Kamala Harris, Alpitruda, three-way S2 summit statement. Even a god of feminist cannot defeat. Bikram, GK by GS, Max TD Swag, Yash Pandey, Abdullah, Fairy Tale, Suhas Reddy, Parasatav Kundu, VM Pai, Tube, Tipu Master, Anand Pai, Bhaskar Kayathwal, Alok Bhatt, Karan Nalawat, hello, H Raptor, Giuseppe Di Fraia, Tanmoy Chakrabarti, Harsh Dubey Komal, Mriganka Bonia, Ishant Singh, Genichiro Ashina. Curiosity, Miguel Diaz, hello. Cosmic Gaming, 87781. Cookie Dur, Joy Mukherjee, Vladimir Chavda, Mohana Ray, Roy, Naga Mokshit, Ralla Avinash, Suhas Reddy, Parasatav Kundu, Neve, Swook Mahdik, Niharika Gupta, Harsh Dubey, so many other people. Random Skull, hello. Shreyas, and so many other people. Zubon Ezang, GK, Ombe Kerikar, hello. And everybody else. I won't be able to greet you all, but let's get going with the questions. I'm going to take questions, first of all, from the comments. And once those are done, I'm going to take some questions from the live chat once those are done. So let us see what questions we have, what questions you have asked in the comments. And let me see how many of those I can take. I'll take as many as possible. What is the first question? It is by Shot4411. And the question is, tell us something about the observer effect. The observer effect of quantum mechanics. I don't know if you guys remember, but there used to be in the 1990s a song called Shy Guy by a lady called Diana King. Very famous song in the 1990s. I was a kid back then. I don't think anyone remembers that today. It's kind of an obscure classic song. But that song is kind of appropriate for the observer effect. Imagine that you have a friend. Imagine you have a friend who is really shy. And this friend of yours behaves differently when he or she knows that someone's watching them. So the observer effect is kind of like that, but it happens in the quantum world. So the observer effect describes how the act of observing something or measuring something can change what is being observed. So, for example, let's say that you're trying to check the air pressure in your bike tire. You have a bike, and you want to check if the pressure is what the pressure is. So you have to take a pressure gauge, you have to insert it, you have to press it into the valve in the bike tire. And when you do that, to check the pressure, a tiny bit of air escapes from the tire when you insert that, right? So this means that the very act of measuring the pressure of the bike tire slightly changes the pressure in the tire. This is an example of the observer effect in the real world that we inhabit, in the classical world, in the everyday world that we inhabit. The tools and the methods that we use to observe or measure something can inadvertently end up affecting and changing what we are trying to measure, what we're trying to observe, what we're trying to study. Imagine you have a glass of water. You have a glass of water, okay? And you want to measure the temperature of this glass of water. So what are you going to do? You're going to take a thermometer, you're going to insert it into the water. Now, I can guarantee you that your thermometer is going to be at a different temperature than the water. Slightly cooler, slightly warmer, whatever. There's no way it will be exactly at the same temperature as the water. So when you put the thermometer in the water, it will slightly change the water's temperature. Okay, so once again, just by trying to observe or measure something, you end up changing the system or changing the thing that you're trying to observe. Now, when it comes to quantum mechanics, the ultra microscopic, the hyper microscopic world, this effect becomes even more noticeable and important. Let's say you got a super tiny particle. Let's say you have an electron, a single electron, and you want to know where it is and how fast it is moving. That's all you want to know. You know there's an electron in a box, let's say, and you want to know exactly where it is and how fast it is moving. So how do you do that? Well, you're going to try and see it, right? You're going to try and bounce light off it. But in the ultra microscopic quantum world, light comes in the form of photons. There are these little packets, or you can say particles of light, massless particles of light that have momentum and energy. So you're gonna take these photons, you're gonna try and bounce them off the electron. But the electron is so small that the very act of a photon bouncing off it is gonna change its position. It's gonna knock it off its position. It will change its velocity, change its trajectory. The electron may even end up absorbing this photon. So just by trying to observe or measure observe the electron or measure its properties, you end up changing what the electron is doing and changing the very nature of the electron. So this is like trying to see what your shy friend is doing, but as soon as you peek at your shy friend, they start acting differently. Okay, so in other words, the very act of measuring or observing something in the quantum world actually changes the thing that you're trying to observe or measure. And that makes it really hard to know exactly what's going on, because the very act of observation changes what you're observing, and it can mess things up. So that essentially is the observer effect. Hopefully makes a little bit of sense the way I have explained it. Next question is by Tech Rumor. How to explain wormholes to children? The universe is a sphere, so why fold paper for the explanation? What is the proof that it exists? Okay, the universe, the observable universe, you can think of it as a sphere, but we don't know if the universe is spherical. Okay, so the observable universe, the cosmic horizon is kind of spherical, and we are at the center. But that's merely what we can observe. The actual universe maybe is most likely way bigger, and we don't know what the actual shape is. But now let's talk about wormholes. What are wormholes? And you don't want me to use the analogy of that sheet of paper and you poke a hole through that, right? Because it's an overused cliche. It's like flogging a dead horse. So okay, so how do I explain wormholes for children? Let's imagine the universe, okay, as a giant bowl of noodles. Noodles, Maggie noodles, ramen, spaghetti, whatever. Imagine that the universe is a big giant bowl of noodles, and each individual noodle, each strand of noodle represents one specific path through space and time. So the universe is this giant ball with a tremendous number of paths through space and time, and each strand of noodles, each noodle is one specific path through space and time. So normally, if you want to go from one end of the universe, one part of the bowl, to another part of the bowl, you have to walk along one of these curved paths, one of these noodle strands. So imagine that you are an ant, a tiny ant, and you are standing on one of these noodles, one of the noodle strands, and you are at one location and you want to get to another location. So you're going to have to crawl like an ant, because you're an ant. You're going to have to crawl over this noodle, and it's going to be a long winding path, and it's going to have twists and turns, and it's going to take you a long time. But what if you have a shortcut? What if there exists a shortcut which allows you to reach the other part of the universe like that? So it's like you found a way to poke a hole through the noodles, and this hole connects two distant parts of the universe bowl directly. So instead of crawling over along the entire noodle, you the ant can just zip into this hole and come out on the other side way faster than if you had to travel the entire long path. So that is kind of a wormhole. In the real universe, the wormhole could theoretically connect two distant points in space time through a shortcut. So it gives you a potential shortcut across tremendous cosmic distances and possibly even through time itself. Let's use a different analogy. Imagine the universe is a giant playground. Okay, kids' playground. And in this playground, you got lots of paths and lots of roads and lots of routes that you can take to go from one place to another in the playground. But these paths and roads and all, they are very long and winding. Now think of a wormhole as a secret shortcut that connects to faraway places in the playground directly. It's kind of like a hidden tunnel. So instead of walking and taking this long, twisting, winding path, you just jump into the tunnel and instantly appear at your destination. Imagine you're playing a video game, and your character in this video game can use a special portal. And this portal instantaneously transports you from one part of the game world into another part of the game world. And you can skip all the obstacles, skip all the dangers, not dangers, you could skip all the obstacles, and it saves you a lot of time. So you have this magic portal which instantly transports you from one part of the game world to another. You skip all the obstacles, saves you a tremendous amount of time. So wormhole works in a similar way. It's like a shortcut like a shortcut through space and time. It allows you to travel vast distances in a very short time. But just like in some video games where portals can be unstable and portals can be dangerous, wormholes, if they exist, might be extremely unstable, and they may require conditions for them to stay open that we don't quite fully understand yet. You may need exotic matter inside the wormhole's throat to keep it open. You may need something even weirder like cosmic strings inside to keep it open, keep the throat open. So wormholes overall are mathematically possible solutions of the Einstein field equations. They are mathematically possible according to the theory of general relativity, but we have not found any evidence that they actually exist thus far. And creating a wormhole would probably require tremendous amounts of energy, and maintaining a wormhole, keeping it open, would also probably require exotic forms of matter and energy that we don't even know are possible in the universe. So that is how I would explain wormholes to kids. Okay, Clasher Abhay says, please explain rocket science. Rocket science, haha. I think this question was asked as a joke, but let me take it seriously. Let's understand what rocket science is. Well, rocket science isn't actually science, it's engineering, it's applied science. And what is the problem we're trying to solve in rocket science, in rocketry, let's say? What you want to do is you want to transport something from point A to point B in a very short amount of time. And ideally, you can use a rocket to deliver a payload from point A to point B on the surface of the planet, or more likely, you want to get into space. So maybe you want to place a payload into Earth's orbit, or maybe you want to go to the moon, or maybe you want to go to Mars, or maybe you want to go to the Andromeda galaxy. So you want to go beyond the Earth. Okay, you want to travel into space. So how do you do that? That's the problem you want to solve. I have this requirement. I want to get into space. So how do I do it? That's the problem you want to solve. And that's where rocket engineering comes in. It's actually rocket engineering, not rocket science. It's not rocket scientists, it's rocket engineers. So what do you do is you need a vehicle that can take you into space. Now, for that, you will have to overcome the escape velocity of the Earth. Or let's say you want to place something in orbit around the Earth, okay? In that case, you don't need to have a speed in excess of the escape velocity, but you need to have orbital speed. So you need to get to a certain amount of altitude, and then you cannot just go straight up. You have to go in that direction, and you have to miss the Earth and constantly fall and all that. So you need a vehicle that can achieve tremendous velocities, that is aerodynamic, which will not burn up because of friction with the atmosphere, the heating of the atmosphere, and all that. So for that, you need the right kind of structure, the right kind of material, which is typically metal and composites. You need the right kind of aerodynamic shape, and you need the right kind of fuel. You need fuel with a very high impulse. Okay, kerosene, which is aviation fuel, won't do. It doesn't have that much impulse. uh, petroleum and whatever else won't do. You need something with much higher impulse. So you could use hypergolic fuels, which are extremely toxic, or you could use simple liquid hydrogen, liquid oxygen, cryogenic fuels, and so on. So all of these problems are solved in a variety of methods using engineering, and that is rocket science. And if you want to travel to other planets and so on and so forth, you have to understand celestial mechanics, which obviously is nothing but a branch of Newtonian mechanics, classical mechanics. You don't need to use quantum theory, general relativity, etc. In that, you may no, you don't need general relativity. You can send human beings safely to the moon and bring them back without ever resorting to general relativity. You can do that just by using Newtonian mechanics. So all of this is rocket science. All right, that is the problem that rocket science seeks to solve, and it has engineering solutions. So you it involves the study of aerodynamics and the application of aerodynamics, the application of various kinds of fuels, multiple staging rockets if required, uh, deployment of payloads into orbit, achieving orbital velocity, injecting your vehicle in a specific orbit, whether it's a polar orbit, whether it is a Lissajous orbit, whether it is what is it called, geocentric orbit, and so on and so forth, or a transfer orbit into a different, maybe lunar transfer orbit or whatever, and so on. Orbital raising maneuvers. There's a whole lot that is involved in all this. So all of this taken together is what is colloquially called rocket science, is actually rocket engineering. All right. Okay, Swapnil Mishra says, why do modern fruits and vegetables look and taste so different from their wild ancestors? And what caused this change to occur? Yeah, it's a good question. I mean, modern fruits and vegetables, they have evolved over time. For example, let me put something on the screen. I mean, there is something called the giant red banana. Check it out. So, the fruits that we are aware of come in a variety of different cultivars and all that. Look at this thing, for example. This is called a casa banana. Look at it. Casa banana. And that looks quite different from the bananas that we are familiar with, but in yet it is a kind of banana. But it's not something that we really use, or are even much aware of. And when it comes to the bananas, the ancestor of the banana plant or the banana fruit was very different from the banana fruit that we are familiar with. It was much smaller, and it had large seeds, and it had very little edible flesh and all that. So it all happened through selective cultivation. When our ancestors thousands of years ago discovered that certain plants have some good qualities, and they are good candidates for food, then they started cultivating them, and they started selectively breeding them, just like we have bred various breeds of dogs. I mean, if you look at the dogs come in so many shapes and sizes. Some don't even look like dogs. I mean, their wolf ancestors would be, I would say, ashamed to imagine that these are their descendants. Those poodles and those chihuahuas and Pomeranians and whatnot, those toy looking like nude what sausage dogs or whatever. I mean, it's hard to imagine that these are descended from wolves, right? But that's the case. So that's what humans are capable of. Over time, we can create various breeds of plants, animals, vegetables, fruits, whatever, as per our requirements and our tastes. So that's what we've done. And obviously, everything evolves over time. If you look at Homo sapiens, the archaic Homo sapiens from Jebel Irhoud in North Africa from 400,000 years ago, I mean, they are anatomically modern humans. They have the same skeletal structure as you and me, essentially, but their facial features are a little more primitive, and with the little larger eye ridges and slightly more, I don't know, different kind of facial characteristics and all that. Uh, so evolution happens over time. It happens naturally, and when the human beings get involved, then evolution can be accelerated by selective breeding. So overall, that's why things change. That's why fruits have evolved and vegetables have evolved, especially those that we humans have been interested in. And then you have things like what the green revolution that happened in India, in which certain cultivars of wheat, certain cultivars of rice were prioritized over everything else. That kind of stunted the natural diversity of various cereals in the country. It kind of put the millets, etc., on the back foot. It will almost make them obsolete. Now they're taking making a comeback. So yeah, that's how it goes. It's all about choices that humans make, which has a long term lasting and very pronounced impact on the way the ecosystem, the environment evolves. So that's why modern fruits and vegetables look and taste different from their wild ancestors. I mean, wheat. Think about wheat. Wheat is a grass. It's a form of grass. Sugarcane is a form of grass, but we selected these plants for certain properties and we bred them, and that's how. If you look at wild wheat, which still exists in some parts of the world, it looks very different from the wheat that we are familiar with. And similarly, wild sugarcane would be much thinner and shorter than the typical sugarcane that we have in the fields for cultivation. So it's because of selective breeding done by humans that all these changes have happened. Next question is by Rajorshi Gon 8396. Why does Australia have such an enormous variety of venomous and poisonous animals as compared to other continents? I think Australian animals get too much of a bad rap. I know there are certain very scary animals. Let's go back to Google. What about the inland taipan? I mean, they have some really. What on earth am I doing? One second. They have some really scary, dangerous, etc. Uh, animals. For example, the inland taipan is probably, I believe, the world's most venomous snake. Perhaps one of the world's most venomous snakes, the inland taipan. That's an Australian snake. Um, it is, etc. Yeah, Australia. Then you have something called the box jellyfish. Box jellyfish. That is another frighteningly dangerous jellyfish. And if you are bitten by that, it can be fatal, and it's extremely painful, extremely dangerous, and you don't want to be near this. Okay, so there is that. Then Australia has various kinds of very scary sharks, including the great white shark, which is the number two predator in the oceans. The great white shark, great white shark, which is the number two predator in the oceans, not number one. And the number one is not the megalodon, it's the orca, the killer whale. What else do the Australians have? They have got what? Redbacks, redback spider, redback spiders, and various other kinds of spiders. I mean, imagine this spider is, as you can see, it's killed a snake here. Yeah. And then what else do they have? What else can I think of? The Australians have a number of very scary, uh, rather scary animals and such species. But overall, if you look at the other animals in Australia, like the marsupials, the kangaroos, they have like at least a couple of species of kangaroos. They have wallabies, they have koalas, and they have all kinds of harmless animals as well. Really harmless animals. The kangaroos are kind of feisty. They are known to box, and they kind of are territorial in nature. They won't be happy, especially the large kangaroos, if you intrude into the territory and so on. But overall, they're okay. Yeah, I forgot the crocodiles, the saltwater crocodiles. Let's put that on the screen. So that's not exactly an Australian crocodile. Saltwater crocodile. That's a crocodile that's even found in India, okay, in the eastern Indian Ocean region, but it is a gigantic crocodile. And this is also found in northern Australia, northern eastern Straya, etc. Very large, gigantic, monstrous crocodile, the saltwater crocodile. And I'm sure I'm missing a few of these wonderful creatures, but that is the deal. But they also have a lot of harmless creatures. So so one thing I would agree with is that Australia has a rather unique animals. I mean, you don't find marsupials anywhere else in the world apart from Australia and Tasmania, right? Marsupials. You had the Hyloceine, the Tasmanian tiger, which went extinct. You have the, what is it called? The red, what, devil? Tasmanian devil, which is also in Australia. Very, it's got a really, really weird way of shrieking at night, really scary. That's why it's called the devil. You have the kookaburra bird that has an incredible vocalization. That too is scary if you are not used to it, and so on. Um, the thing is that Australia, if you look at the map, okay, we haven't seen the map today. I usually don't crack out the map in science streams, but let's do it. Maps. Let me open that and put that on the screen. Give me a second. So what we're gonna do is we're gonna take a look at the map. I'm gonna go to the globe view. Okay, so we're going to look at Australia, and you can see that it's kind of isolated. It's near Papua New Guinea, Indonesia, but it's kind of isolated in the southern hemisphere, far away from most other, large real estates, essentially. And the animals here have evolved mostly in isolation from other parts of the world. Um, so maybe that's the reason why they have evolved differently in Australia. And Australia also has a very unique kind of climate. It has a cold climate in the south. It has forests and mountains. It even has snow somewhere or the other, I believe in New South Wales. And it has a very large desert region. As you can see, it's barren. A lot of it is barren. So it's got a very unique terrain and climate. And that's why I would imagine the animals have evolved here in isolation for hundreds of thousands of years. And that's why they have evolved in rather unique ways. But I wouldn't say that Australia has more dangerous, venomous, poisonous animals and species than, let's say, other parts of the world. In India, you have a whole lot of poisonous, scary animals. You have the cobra, the standard Indian cobra, you have the spectacle cobra, you have the king cobra, you have the Russell's viper, you have various kinds of pythons, you have scorpions in India, rather scary scorpions and whatnot. I mean, you've got really scary animals in India. You have gigantic bears, at least three species of bears we have in India. Bears look very fluffy and very nice, but trust me, you don't want to be near bears. Bears can be really, really dangerous. They're incredibly powerful. Tigers, stay away from bears. So you have that, you have tigers, obviously, you have lions in India, you have hyenas and whatnot. So it's not like Australia is something special. Every part of the world has its predators and all that. But it's true that Australian animals have evolved differently and they have rather unique species over there because of the relative isolation of Australia and the unique kind of climate and terrain that Australia is endowed with. Okay. Anti-Human says, what makes you say that the American military or multinational corporations have AGI, artificial general intelligence, in their labs? If they have it, then why don't they deploy it? Okay, why do I say this? It's because we have known throughout history that whenever new technology emerges, it is always used first by the military and the government of the nation or culture or civilization where the technology emerges. And technology is guarded jealously. It's not distributed out freely for everybody to use. It is guarded jealously. And history tells you that whenever there have been conflicts, it's always the technologically superior side that prevails. In warfare, it's always technology and superior tactics that prevails, not superior bravery. I mean, in movies, they talk about bravery of humans and all that, but in the real world, it's not about bravery. It's about superior technology, tactics, strategies, and all that. So when you have something superior, you're gonna hoard it. You will not make it available to the rest of the world. You will not even speak about it. Think about the stealth technology that the Americans had since the 1960s. It was first spoken about in public in the late 80s, and the first time it was announced, shown to the public, was probably the early 90s or thereabouts. But they had it for decades. What about MIRV technology, multiple independently whatever targetable vehicles? Uh, those also were classified technology for such a long time. There is so much that has been classified for a very long time. There is technology today that you have never heard of, that I have never heard of, but it exists. So the cutting edge, bleeding edge technology is always kept secret. Okay, why do we have so many UFO sightings? Maybe these are futuristic aircraft that are being tested, and sometimes people spot them, right? So there's always that. I mean, history tells us, history of the 20th century tells us that so much technology was kept hidden for a very long time. Now, so that's why I believe that if AI is known to exist today, then what we are seeing is merely the tip of the iceberg, and what really exists out there, deep under the secret layers of secrecy in the US military or department of whatever thing, military or various multinational corporations or American corporations, I imagine what they have is at least 100 times more powerful, maybe many orders of magnitude more powerful, which would essentially mean artificial general intelligence, or even ASI, artificial super intelligence. That's why I say I say that it is possible that this may exist. Now the question is, why haven't they deployed it? My dear friends, who tells you that they haven't deployed it? If they have it, it may be deployed. Like I said, they may have deployed various futuristic aircraft, and sometimes you get some glimpse of it, and you think it's a UFO. Maybe lots of such things have been deployed, and we are not aware of them. When you deploy something, you don't announce it to the world and show it to everyone. You deploy it stealthily. Maybe everything is being observed right now. Maybe every government is compromised right now. Maybe every bank account is compromised right now. Maybe every prime minister and president, whatever they're doing right now, they are being monitored in real time. Maybe every nation's nuclear program is being monitored in real time. Maybe everything is being monitored in real time, and everything is known, but we don't know about it because it's secret. Maybe it's all deployed. Think about it. I mean, use your thought process, use your imagination. And I'm not talking about imagining magic and fantasies and fairy tales. This is all logical, it is consistent with science. So it is possible that AGI already exists. It is also possible that ASI may already exist, artificial superintelligence. And if it exists, it is being used and it's being deployed, but you don't know about it. All right? Anand Chandrasekharan, 1969, says, I'm working in an IT company and already see that AI is gradually replacing human effort and even causes job loss. Do you think that in the future, AI, artificial intelligence, will supersede human minds and become a company friendly resource? In that case, is the AI easily manageable and cost saving? Um, I see it rather differently. I agree with you. AI is already being used widely. Its use is widespread. The stupidest. See, look, I'm sorry, I shouldn't say that. Look, in a company, the real performers, the employees. See, let's say you have 100 employees in your company. That there's going to be 10 guys or girls who are the real performers, who really drive whatever's happening. So about 5 or 10 are the real performers. Maybe 20 are the top level talent. Then another 20 or 30 are okay level talent, and then there'll be like 30-40% who are absolutely they should be replaced. That's generally how it is. So there is a significant percentage, no matter which company you're in, of you will have employees, 30-40% at least, who are not real performers and who are actually redundant and replaceable at any given point in time. Those people are the ones that AI will essentially can replace right now. There's so much that AI can do that essentially makes people significantly redundant, especially those who are not creative and not really talented and not really hardworking. And even if they are hardworking, if they don't have that special talent, then AI can replace them right now. I mean, if you want to do research today, then you don't need to hire research assistants. Just use AI. Whatever Chat GPT 3.5 or 4.5 or Grok or Claude or whatever. These AIs can do a stellar job. as research assistants. You got to get the paid version, and you can do as many queries, I suppose, as you want. So yeah, AI is already beginning to make human beings redundant, especially the low skilled human beings. And once you have robotics coming into the picture, that's going to make a lot of the labor force redundant. And because robotics is way more efficient than humans, and because robots don't need to sleep, they can work 24/7. So it's gonna be a paradigm shift in uh, in the workforce. So yes, I agree with you that AI is gradually replacing human effort. It's causing job losses already. Uh, so do I think that in the future AI will supersede human minds? Yes, yes. Very soon there's going to be very few fields in which AI cannot outperform humans. Right now, AI can create music. AI can create all kinds of art. I mean, you can tell, if you have the eye for it, that this is AI art. But for most people, it's good enough. I mean, it's beautiful art. You can produce art in the style of Van Gogh or Picasso or whoever you want. Any kind of art, you can just give it what you want, and it's going to create art in the shape and form and in that style. Music, I'm sure the music isn't like soul stirring music, but it's good enough music. So it's going to put all but the best artists out of commission, and so much more. So we already are seeing this. And when it comes to tasks that don't require a lot of intelligence, AI is already there. And soon you will have AGI, which means AI that is like which is the equivalent of a person with 140 150 IQ. And that person can do essentially anything: speak any language you want, translate in real time, give you ideas, disagree with you, and give you better suggestions, and things like that. That's AGI, artificial general intelligence. And then soon you will have ASI, artificial super intelligence, which is way beyond AGI. It's like having a person with an IQ of 300 or 400. And then it will supersede anything you can do. It'll go way beyond what the human mind is capable of. It's like Einstein on steroids, and creatine, and every drug you can imagine. Okay, you multiply Einstein and Ramanujan and Leonard Euler and everybody, and you multiply that by 1,000. Maybe that's what your ASI is going to be like. So that's what it will do eventually. Will AI become company friendly resource? Look, if your company is paying for the AI, if your company is a customer of an AI company, then it may not really be company friendly. It's gonna be it's gonna be friendly to the company that created it, that owns it. But if your company has created the AI and owns the AI, then it's gonna be hopefully in your control. Okay, so it's not gonna be friendly to anyone apart from those who have created it and own it and hopefully control it. Okay, it may not be easily manageable. It will definitely be cost saving. It may cut all your costs, but it will make people immensely rich. Only those who own the AI. Everybody else will be out of job, and then they'll be wonder what is going to be done about them. Yeah, and we may soon be there. AGI ASI may already exist in secret. So we may be at the cusp of the greatest inflection point in human history, and we probably don't. We are unable to see what's coming. It could come anytime. So yeah, that's how I see it. Malik says, is it possible to connect large AI models to track rocket pathways, projectiles, and their motion and improve it? Absolutely. For large AI models, projectile motion is trivial. Large AI models can model entire weather systems. They can model climate. They can look far into the future, like weeks into the future, months into the future, when it comes to predicting climate patterns. You take AI, you merge that with supercomputing capabilities, and AI obviously it needs a tremendous amount of resources, computing resources, GPUs, and all that. It can do that. So when it can do that, what are rocket pathways and projectile motion? That's child level stuff for AI. Yes. So what AI will be used for is wargaming, nuclear warfare. Okay, let's say I launch, hypothetically. Okay, let's say I am a superpower and I launch the first strike on he who I hate the most. Okay, and he who I hate the most has more nukes than me, and he's going to retaliate. So how do we war game it, and in what by what way by what strategies, by employing what strategies and tactics can I turn this into a war, a nuclear exchange that is survivable for me but not for him? So that's the kind of wargaming AI can do, and it can find, I'm sure, solutions that nobody may have thought of. So projectile motion, rocket track paths, and all that is trivial for AI. That it can do in its sleep, essentially. All right. Pradyumna Nittala says, what are cryogenic engines? What makes them different from other engines? And why are they used only in rockets? What are cryogenic engines? So essentially, cryogenics and cryogenic engines are engines that use extremely low temperature fuels. Okay. Cryogenic engines are rocket engines that use propellants, fuels that are in the liquid state and that are at extremely low temperatures, like minus 150 or something degrees centigrade. So, a very standard, typical cryogenic fuel are liquid hydrogen as the fuel and liquid oxygen as the oxidizer. You bring them together, you spark the ignition thing. It's going to give you a tremendous amount of energy as the exothermic reaction energy is the output, and the waste product that is expelled out is simply water vapor, H2O. Okay, so that is a great example of a very standard cryogenic fuel: liquid hydrogen as the fuel and liquid oxygen as the oxidizer. Okay, so that's what a cryogenic engine is. Now, what are the key differences of cryogenic engines from other engines? So the first very clear difference between cryogenic engines and other standard engines is that the cryogenic engines are they operate at extremely low temperatures. So probably usually below minus 150 degrees Celsius. So when you see a rocket, whether that is on the launch pad and it's waiting to be launched, you will see it is sweating and it is steaming, right? All this steam is coming off it. It's not steam, it is extremely cold condensation. And when the rocket, because the fuel inside is extremely cold, minus 150, minus 160, minus 170 degrees Celsius. So it's gonna, you know you will have a layer of ice that forms on the surface of the rocket. And if the air is humid, then you will see all the entire rocket steaming away. And when the rocket finally takes off, you will see all this ice and everything falling off it. So that's because of the incredibly low temperature that the rocket has, because that's the cryogenic propellant. So the first key difference is the temperature, tremendously low temperatures. Second, efficiency. Okay, so cryogenic engines offer extremely high specific impulse, which is a measure of the rocket's efficiency. And it has very high specific impulse compared to other liquid or solid propellant rockets. So if you have a rocket that uses let's say hypergolic fuels, which is solid propellants usually, or some other fuel, let's say hydrazine or something. Hydrazine is not bad overall, but cryogenics are they have higher specific impulse, higher efficiency. Now, if you have a rocket engine, which is extremely cold fuel coming in and an extremely hot exhaust going out, then you need extremely sophisticated systems for storing the propellant, the liquid propellant, liquid hydrogen, liquid oxygen, for pumping the propeller into the engine, for cooling the engine, because the moment the engine ignites, it has extraordinarily high temperatures. So it's gonna need a tremendously sophisticated set of systems to do this. So it's extremely complex. Okay, so that's the deal with the cryogenic engines. So it's primarily used in rockets. Okay, because of the high performance and because of its efficiency when it comes to space applications. And the cryogenic engines are typically not used in other vehicles, other applications. First of all, because storage is very challenging. Storing liquid hydrogen and liquid oxygen at incredibly low temperatures is almost impossible for day-to-day use. How do you do that? Okay, it's almost impossible in everyday applications. um Secondly, the availability of these propellants. I mean, cryogenic propellants, you can't go to a gas station and get liquid hydrogen, liquid oxygen, because it's not readily available at all, because it needs to be kept at incredibly low temperatures, and it takes a lot of effort and various specialized processes to to separate hydrogen and oxygen from water and all that. So the propellant isn't readily available, and obviously the engines are incredibly complex, which means they're incredibly expensive, very costly. So these systems are way too expensive and way too complex for day-to-day applications, non-space applications. And these are the reasons why cryogenic engines are only used in rockets and probably nowhere else. Got it? Karan Nalawat says, what are black holes made of? Is a black hole really a hole in the fabric of space-time, or is a black hole a solid object just like other planets? Yeah, that's a great question. What's a black hole made of? Well, we don't quite know. But I could construct a black hole out of anything. Look, when it comes to, let's say, the simplest black hole of all, which is a non rotating, uncharged black hole, which is called a Schwarzschild black hole, which is like almost perfectly spherical. You can construct that out of anything. You can take a bunch of protons and neutrons and electrons, dump them into a region of space which is smaller than the Schwarzschild radius of the total mass, and you have a black hole. You can take a bunch of neutrinos and do that. You can even take a bunch of photons, which are massless, and create and construct a black hole out of them. I'm talking about a Gedanken black hole, a thought experiment black hole. I can use paper and pen and take a bunch of photons in my mind's eye and create a system. Okay, let's say I have a bunch of photons. It's a photon gas. You want to know the properties, the statistical properties of a bunch of a gas of photons. Look up Landau and Lifshitz, one of the books, and it will tell you exactly what the properties are like, the temperature, pressure, all that of the gas of photons. You take a gas of photons in in a spherical container, which with perfectly reflecting walls, and you contract this container adiabatically. And when the container, the radius of the container is less than or equal to the Schwarzschild radius of the gas of photons, you have a black hole. So that's a thought experiment. It's a Gedanken experiment, but I can construct a black hole using just photons with that. Okay, and that's the kind of mind games you play when you're doing research in quantum mechanics or even studying quantum mechanics. So a black hole could be made of anything. Essentially, we don't know what's inside a black hole. That's the problem. There's an event horizon around the black hole, which is a boundary that is completely opaque. We don't know what's inside. You can throw anything into it. You can throw pizza into it. You can throw spaghetti into it. You can throw a car into it. You can throw photons. You can throw whatever into it, antimatter, and you won't know what happened to the matter, the material, once it crossed the boundary. So from outside, a black hole has, like they say, no hair. It is known by only three parameters: mass, charge, and angular momentum. That's it. And for a Schwarzschild black hole, it doesn't have charge, it doesn't have angular momentum, spin. It only has mass. So we don't know what's inside. But if you are playing the thought experiment game, then you can construct a black hole from the inside out. And as long as that black hole you're constructing in your thought experiment is not a micro black hole with quantum properties, it's a large black hole with classical properties, then you can play around with it and get good results. So, for example, the radius of the sun is about 0.7 million kilometers. So the sun has a diameter of about 1.4 or so million kilometers. The black hole at the center of our galaxy, the Milky Way galaxy, there is a black hole at its center. It's a supermassive black hole. It has a few million solar masses. It's called Sagittarius A star. Now, that black hole has a radius of about 14 million kilometers. Okay, that's about 20 times the radius of the sun. That's how gigantic that black hole is. It's a very cold black hole, and it's a classical object. It's not a quantum object. So if you want to create that sort of a black hole through your thought experiment, then you can construct it out of pizza. You can construct it out of cheese. You can construct it out of anything you want. But as far as we know, because of the limitations of general relativity, and because we don't have a quantum theory of gravity, we don't quite know what's inside a black hole and what the internal structure is like, and therefore we don't know what it's made of. It could be made of a bunch of strings, or it may be made of a bunch of fuzzballs or whatever. Yeah. And is it really a hole in this fabric of space-time? Well, it's not really a hole. Okay, it's not a hole. It's not like a hole would be like a wormhole, an Einstein-Rosen bridge. That's not what a black hole is. It's just called a black hole. It's not even black, actually. It's transparent. It's transparent. And it distorts the fabric of space-time because of its gravitational effects on space-time. Is it solid? I kind of, I've always visualized a black hole as a drop of liquid. I don't see it as a solid object. I've always thought of a black hole ever since I've been playing with black holes. I've always thought of black holes as drops of fluid, as containers of fluid, some kind of fluid. So I don't think black holes are solid. Just like the sun isn't a solid object, is it? The sun isn't solid. The sun's density is greater than that of water. So the sun is like a drop of fluid in a sense. So black holes also, I think of them as drops of fluid. They certainly cannot be considered to be solid objects as such. I don't think any physicist would think of black holes as solid objects. I've always thought. I mean, I haven't thought about this for a while until I saw this question. I don't think I've always thought of black holes as drops of some kind of fluid, a different kind of fluid, not water, but denser, incredibly different fluid, but fluid drops. Okay. Okay, Sanskritic Yash says, we know that red shifting occurs when a light source and observer move away from each other. Or maybe the observer is just where he is or she is, and the light source is moving away. Okay, the Doppler effect, right? Redshift. There's also evidence of light that originated from the young universe that's so redshifted that it has now reached infrared wavelength. So, is it possible for light to get so redshifted that it reaches the wavelength of radio waves multiple meters in length? Also, is there an upper limit to the wavelength of light? All right, we're talking about redshift. So, redshift is when you have a wave, okay, let's say a wave of light, and it gets stretched out. So, there is redshift. If it is blue shifted, it gets squeezed and its frequency increases and the wavelength shortens. So that's what happens. Now, how is the light redshifted? If you have the source of light moving away from you, or if it is static and you are moving away from it, then the waves, the light waves, appear to be redshifted. Okay, they appear to be have longer wavelengths than what they had when they originated from the source. That's just standard Doppler effect. Now, redshift can also happen because of the expansion of the universe. So the universe itself is expanding, and we don't quite know what is footing the bill, the energy bill of the expansion of space-time. Maybe the energy is coming from the redshift because it's being taken out from the photons that exist in the universe, and that's why they are getting redshifted. That's one way of looking at it, perhaps. So the photons, the of the afterglow of the Big Bang, the cosmic microwave background radiation photons are tremendously redshifted. They are redshifted into the millimeter wavelengths, microwaves. So yes, they are tremendously shifted, and some of them, some part of the CMBR spectrum is definitely in has the wavelength of various kinds of radio waves. Yes, so it certainly is possible. In the future, as the universe expands even more, it will eventually happen. What will happen is that the CMBR, cosmic microwave background radiation, it will eventually get redshifted to wavelengths of multiple meters, tens of meters, maybe kilometers, and it will be almost impossible or next to impossible to detect them. It will happen. Yes, so that is correct. um, so yes, it is possible for light to get so redshifted it can reach the wavelength of radio waves. It can reach a wavelength of multiple meters, multiple kilometers in length, and there is no upper limit to the wavelength of light. I'll tell you what's the upper limit of the wavelength of light. It's infinity. And when a light wave is redshifted to infinity, it means it is redshifted out of existence. And that can happen when light, you don't need, I mean, it can happen when a photon of light or a wave of light comes in the path of a black hole. And if it did if it so a black hole is a center and an event horizon, and the closer your light wave comes to a black hole, the more redshifted it gets. Okay, because that's okay. I'll not get into how it happens, the mechanism, but it gets redshifted. The effect of gravity on light, the bending of light, and all that. And there's a quantum mechanical effect in that as well. But if the photon touches the event horizon tangentially, it gets redshifted out of existence, which means that its wavelength becomes infinity. So that is the ultimate upper limit to the wavelength of light, infinity, which means that the photon gets redshifted out of existence. It ceases to exist. Okay, Aditya says, why does a moving charge produce a magnetic field? Why does a moving charge produce a magnetic field? Now, how do I explain this? I could explain it the physics way, but I could explain it a different way as well. So imagine you're standing, okay, just standing, and you're holding a water balloon in your hands, a balloon filled with water, and you're just standing still. So when you're standing still, the water inside that balloon is just sitting there. Now think of this water inside the balloon to be like an electric charge at rest, because you're not moving, you're not running, you're just standing still. So this water inside the balloon, think of it as an electric charge, and it is not moving, it is at rest. Okay, now let's say you start walking with the water balloon in your hand. You start walking, I'm walking and I have the balloon in my hand. So as I walk slowly, the water inside the balloon sloshes around a little bit. Okay, sloshes. So this sloshing is like what happens when an electric charge moves. And in the world of physics, when an electric charge moves, it creates a special kind of sloshing in the space around it. And we call this sloshing a magnetic field. Now I was walking and there's a little bit of sloshing, right? Now let's say I start jogging. I'm jogging now. So there is more sloshing. The sloshing is more vigorous. And then let's say I start sprinting at the highest possible speed. And then there's a tremendous amount of sloshing that's going on inside this balloon. So the faster the charge moves, the stronger this magnetic field becomes. Just like how running faster makes the water inside the balloon slosh more and more vigorously. Okay, so that is kind of how a magnetic field is produced when an electric charge is in motion, and this magnetic field circles around the path of the moving charge, kind of how the water might slosh around, swirl around in a circular motion inside the balloon as I'm running. So whenever there is electricity flowing through a wire, which is just a bunch of moving charges, you'll always find that there's a magnetic field that's created by this process, and that magnetic field is surrounding the wire. So a moving charge produces this magnetic field. Now let me get into the physics of it, very basic. The Your moving charge produces a magnetic field because of the fundamental connection between electricity and magnetism in nature, and also and this phenomenon is actually explained by special relativity and electromagnetism. So what happens is that when a charge moves, its electric field appears different to a stationary observer because of relativistic effects, special relativity. I'm not talking about general relativity here. So your moving charge and its electric field appears different to a stationary static observer because of special relativistic effects. And this relative motion causes the electric field to be perceived partly as a magnetic field by the stationary observer. And this resulting magnetic field that is observed by the stationary observer, it forms circular loops around the direction of the motion of the charge. And the strength of this magnetic field depends on the velocity of the charge and the strength of its electric field. So the basis of electromagnetism and the basis for the production of a magnetic field by a moving charge is special relativity. And this explains why electric currents, which are moving charges, generate magnetic fields around wires. Okay. All right. Next question is by Rohan. What is the relation between the cosmological constant, which Einstein said was his biggest mistake, and dark energy and dark matter? So first of all, there's no relationship between the cosmological constant and dark matter. But it has something to do, or maybe a lot to do, with dark energy. So these are closely related concepts in cosmology. First of all, what is this cosmological constant? This cosmological constant was originally introduced by Albert Einstein in his field equations, in the Einstein field equations of general relativity. And he introduced this constant to allow for a static universe, because he imagined that the universe should be static. It should not be expanding or contracting. It should be static. Because in the 1910s and 1920s, the entire world believed that the universe is a static universe. It's not expanding or contracting or anything, it's static. So Einstein introduced this cosmological constant in his field equations to allow for a static universe. Okay, and this cosmological constant, this term, represents a constant energy density that permeates all of space. So that is what the cosmological constant is. Now, what is dark energy? So dark energy is a hypothetical form of energy that's believed to be responsible for the accelerating expansion of the universe. We discovered that the universe is expanding. We know that the universe is expanding, but in the 90s, I believe, 1990s, we discovered that the expansion of the universe is accelerating. Okay, somewhere around that time. And then this dark energy had this hypothetical form of energy, which is now called dark energy, had to be proposed, which is believed to be responsible for this accelerating expansion of the universe. So that is cosmological constant, that's dark energy. And now what's the relationship? So now the cosmological constant is often interpreted as a form of dark energy. In modern cosmology, the cosmological constant is considered to be the simplest mathematical model that explains dark energy. So Einstein had initially added this term, the cosmological constant, to his equations to create a static universe model, because the prevailing view at the time was that the universe was static, unchanging. But in the 1920s, 1930s, Edwin Hubble discovered that the universe is expanding. And this made Einstein's static universe model and the need for the cosmological constant, it made that unnecessary. And Einstein then removed the cosmological constant from his equations. And he is reported to have said that uh, that was his biggest blunder. Introducing the cosmological constant in the equations was his biggest blunder. So Einstein regretted not trusting his original equations, which naturally allowed for an expanding universe. But now that we have discovered that the expansion of the universe is accelerating, that this discovery led to the revival of the cosmological constant, this concept, as a potential explanation for dark energy. So Einstein's mistake is now seen as a very prescient addition that anticipated the need to explain the accelerated expansion of the universe. So the term that he had introduced for a specific reason, he then removed it, and now it is back, and it seems to have a different purpose and a completely different role to play. But that's what it is. So that is the relationship between the cosmological constant and dark energy, but not dark matter. Trendy Clips says, is making a super collider really worth it? Can it lead to a disaster like nuclear power plants? Well, super colliders aren't dangerous the way nuclear power plants can potentially be dangerous. I mean, we've had some accidents in the past when it comes to nuclear power plants. We've had the 7 Mile Island accident in the United States. We had the Chernobyl disaster, which probably is the worst accident, a nuclear accident till date. Then you had Fukushima because of the 19 because of the 2011 earthquake, and so on. There may have been other smaller instances as well, accidents as well. So there is a certain possibility or probability of nuclear radiation leaking out or whatever in a nuclear reactor. And as long as the right precautions are taken, nothing happens. Hopefully. Now, when it comes to colliders or super colliders, there's no nuclear radiation involved in these. Colliders are simply gigantic vacuum tubes with tremendously strong magnets around them that accelerate particles to almost the speed of light, and then they accelerate two beams of particles in different directions, opposite directions, and eventually collide them in a collision chamber with a whole array of instruments around them. And then you want to see what comes out of the debris of the collision, the gigantic smash up, and hopefully you discover new particles, because the energy of the two beams is so incredibly high that it may end up creating particles that we haven't discovered or observed before. So that's what a super collider does, and there is no danger of it creating some kind of nuclear accident, because there's no nuclear radiation involved at all. One of the dangers that people spoke about before the LHC became operational, I remember in the 1990s, I had written an article about this, defending the LHC. So there was this group of scientists who was petitioning that the LHC should not be made operational, because there was a view that at the time the possibility was being explored that the LHC would be able to create mini black holes, maybe one per second, one mini black hole per second, micro black hole per second, in because of the collisions. And then the danger was that what if these black holes start absorbing, they touch the walls of the collider, and they just gobble up the Earth, and the Earth would cease to exist. That was a danger, right? And I remember in what 1910, what not 19, so I'm not, sorry, I'm not that old. 2010 or something, 2008, 2009 or something, I had written an article about this, and I demonstrated that it is impossible for that to happen. I'll not get into that now. Let's come to the question. Okay, so is making a super collider really worth it? So a super collider, what you call a super collider, has to be something that has greater energy of its beams, of its collision beams, of the colliding particles, than the LHC. Maybe an order of, I don't know, 10, 100 more times more or something like that. So why would you do it? So let's examine the pros and cons of creating a super collider. So if you have a super collider, which is way more powerful than the Large Hadron Collider, then you can explore higher energy scales. A more powerful collider can probe higher energy scales, which can potentially discover new particles or new phenomena beyond the standard model. And that is what we hope for. We have the standard model, but we want to discover, we want to go beyond that. So a super collider could potentially, possibly discover new particles and phenomena. And even if it doesn't discover new phenomena or new particles, it will definitely provide more precise measurements of known particles and known interactions, including the newly discovered Higgs boson. It's still newly discovered, right? So even if nothing new is discovered, it will definitely give us more precise measurements of known particles and interactions, and it will help us understand the Higgs boson and other such particles better. And obviously, if you develop such a machine, it will lead to various kinds of innovations in accelerated technology, superconducting magnets, detector systems, and so on and so forth. So technological and engineering advancements, which is not something that you really want. You actually want, if you're building a super collider, you want to make fundamental progress in physics and fundamental discoveries, new discoveries. So these are the pros of creating, of building a super collider. What are the drawbacks? What are the cons? So the most obvious con is the cost. So the Large Hadron Collider is probably the most expensive instrument or machine ever built, and building a new, more powerful collider would be incredibly expensive, extremely expensive. And that expenditure will definitely divert resources away from other scientific endeavors. So that's a big drawback. Then secondly, there's no guarantee that this new collider would make any groundbreaking discoveries, because we have no idea, we don't know for certain what exists at higher energy scales. We're just probing in the dark, like blind people. We have no idea what exists at higher energy scales. So there is absolutely no guarantee that this new collider will make any kind of groundbreaking discoveries. I mean, the Large Hadron Collider was supposed to discover all kinds of things, supersymmetric particles and whatnot, micro black holes. Nothing. The only new thing it discovered was the Higgs boson. Nothing else. So from that perspective, it's been kind of disappointing. Okay. So there's that. So there's no guarantee of any new discovery. And then your new collider will require tremendous amounts of energy to operate. The Large Hadron Collider, its energy bill is, I think, equal to that of a small country. Okay, just one instrument. Imagine you have a super LHC or a super collider. It's gonna be the energy equivalent of a medium-sized country, perhaps. Imagine that, right? So where does that energy come from? You're going to have to provide more energy, generate more energy. How do you generate more energy? Europe is already facing an energy crunch. What are you going to do? You're going to burn coal. They already shutting down the nuclear reactors in Germany and wherever else. So there's environmental concerns and all that. If you have to burn coal to do that, or maybe you have to get the energy by burning gas and you get it from Russia. That is taboo right now. And we'll not talk about geopolitics right now, but there you have it, right? And so on. So overall, I would say that because there is no guarantee of any new discovery, and because of the incredible costs involved in building the collider and then operating the collider, overall, I think it's not a great idea. If you have that much money to throw around, why not fund other experiments and fund other research? There's so much research that needs to be done in so many different fields. So I would say if I were to make the decision, if I had the funding, I would not build a new collider. I would maybe build a few telescopes on the moon, or I would fund other scientific research. There's so much more that needs to be funded. So that's how I see it. Yajnavalkar 9449 says, what happens if someone crosses through the center of the so-called ringularity, the ring-shaped singularity of zero thickness, at the center of a spinning charged black hole, such that the crossing happens perpendicular to the plane of the ringularity without touching it? In other words, what happens if we enter a spinning charged black hole along the axis of rotation of the black hole? So what he is saying, or she is saying, I'm not sure who it is. Okay, let's say you have so you're talking about a black hole that has mass, it has charge, it has angular momentum, which is spin. So it is spinning just like the Earth spins around its axis, the north-south axis. Okay, that's the axis of rotation, and we are going to enter this black hole along the axis of rotation, the north-south axis, maybe along the North Pole or the South Pole. That's what we are talking about, and that's what the question is about. So first of all, let's understand what kind of black hole we're talking about and how many kinds of black holes exist. So the simplest black hole we can think of is a black hole that has mass, it has no charge, it has no spin or angular momentum. Okay, so this is called a Schwarzschild black hole. It has a completely spherical event horizon. Then you have a black hole that has mass, it is spinning, which means it has angular momentum, but it doesn't have any charge. So such a black hole is called a Kerr black hole, Kerr. It has mass, it has angular momentum, spin, it has an oblate squashed event horizon, and it has an ergosphere, which is a region outside the event horizon where objects cannot remain stationary. That's a Kerr black hole. Then you have black holes that have mass and charge, but are not spinning. That's a Reissner-Nordstrom black hole. Okay, so these black holes are mass and charge. They have two spherical horizons. There is the event horizon outside, and there's a Cauchy horizon inside. And inside the Cauchy horizon, weird stuff happens. Okay, and then you have a black hole with mass, charge, angular momentum. That's a Kerr-Newman black hole. It has mass, charge, spin. It has a complex structure with an ergosphere and multiple horizons, an event horizon and a Cauchy horizon. And now the black hole we're talking about is the Kerr-Newman black hole, and it has a singularity which is not a point singularity, it's a ring singularity. It's called, you could call it a ringularity. Okay, so this is the Kerr-Newman black hole that we're talking about now. So if somebody were to enter were to cross through the center of the spinning charged black hole along the axis of rotation, then if you were to enter through there, you would experience some very strange effects because of the extreme warping of space-time. But you may not necessarily be destroyed immediately, because if you go through the axis of rotation, you will avoid the ringularity, the ring-shaped singularity. Okay, you'll go through it, but you will not touch the singularity. You will not touch the ring. Just go through it. So, so you will avoid direct contact with this ringularity. You're going to cross the outer event horizon, and you may not perceive anything if the black hole is large enough. You may not even know that you've crossed the event horizon. Then you will go inside. You will continue inside, and then you will pass through the inner horizon, which is called the Cauchy horizon, Cauchy, Cauchy horizon. And once you pass through the Cauchy horizon, you enter a region where conventional physics breaks down, and you no longer know what's going to happen. Okay, so over here in this region, causality breaks down, or causality becomes confusing, and you may end up seeing multiple versions of the universe. You may even end up seeing your own past. So that's what happens when you go past the Cauchy horizon. And once you cross the outer horizon, the event horizon, you can no longer communicate with the outside universe, and so on. So inside the Cauchy horizon, everything goes strange, and the causality breaks down. But you are gonna, if you go through the axis, along the axis, you're gonna bypass the singularity. You will avoid the ringularity, but you may end up getting spaghettified. So you will definitely, depending on the size of the black hole and the size of the ringularity, you will experience tidal forces. If the ringularity is small and not too large, you may experience extreme tidal forces and extreme electromagnetic effects because of the charged nature of the black hole. And you may get stretched out into very long strands of spaghettification. And it's even possible that the region inside the inner horizon, inside the Cauchy horizon, may have negative energy states. So you may experience extremely strange, bizarre effects. You may see multiple versions of the universe. You may encounter white hole like phenomena. You may even exit the black hole into another universe, or maybe another part of the universe, which is the uh, a wormhole situation and all. So this is all highly speculative. Okay, we don't exactly know what will happen, but we know that causality breaks down here inside the Cauchy horizon. And quantum gravitational effects also become important near the singularity, but we don't have a theory of quantum gravity that explains what happens. So essentially, this is something that we don't quite understand because of the limitations of known physics. While crossing the center of the spinning charged black hole along the axis of rotation, you will definitely theoretically avoid the ringularity, but you're going to pass through regions of space-time where our current understanding of physics breaks down, and the actual experience will probably be stranger than science fiction. That's what I could say. Okay, once again by Yajnavalkya. Is it possible that we may be living in a false vacuum which is metastable but is not in its most stable state? If that is so, is it true that such a false vacuum can decay anytime, such that the influence of the decay happens with the vacuum speed of light, and thus we may not be able to even detect the decay? Even in principle, if the false vacuum decays, it would likely mean the end of all matter in the universe after the decay of the false vacuum happens, wouldn't it? Okay, what do we mean by vacuum decay? What are we talking about? What is a vacuum? What is a false vacuum? We have to understand this first, right? What is a false vacuum? What do we mean by that? What do we mean by by the statement that the universe is in maybe a false vacuum or a true vacuum? We're talking about the Higgs boson and the Higgs field here. First of all, understand that this has everything to do about with the Higgs field. So we've all heard of the Higgs boson, right? It is completely incorrectly called the God particle. There's no it's not a supernatural thing. It's journalists who have given this term. to this Higgs boson. But the Higgs boson is a particle that endows the universe and the particles in the universe with mass. And the more strongly a fundamental particle interacts with the Higgs field, the more massive it is. And the less strongly a particle interacts with the Higgs field, the less massive it is. And some particles simply don't interact with the Higgs field, which is why particles like the photon are massless. Okay, so the Higgs boson has a field corresponding to it, which is the Higgs field, and this Higgs field permeates the entire universe, according to quantum field theory, and so on. So this Higgs field is a scalar field that exists in a vacuum. And what's a scalar field? What's a vector field? What's scalar versus vector? A scalar quantity is a physical quantity with only magnitudes, but it has no direction. So mass is a scalar field. Electric charge is a scalar field. Is a scalar quantity, and so on. And the vector quantities are physical quantities that have magnitude as well as direction, force, weight, etc. So the Higgs field is a scalar field. Okay, and the Higgs field has potential energy. Now let's take a look at what the Higgs field looks like, because the Higgs field has the shape of a Mexican hat. The Higgs potential, Higgs field. Let me put that on the screen. Higgs field, Higgs potential. So it has the shape of a Mexican hat, so to say. Okay, kind of. You see that? That's what the field is shaped like. Now you can see it has a hill, and it has at least one valley, maybe multiple valleys, and so on. Right? Uh, so so that's what the Higgs field is. It has the shape of a Mexican hat. Now there could be multiple ground states of the Higgs field, and the ground state means the most stable state, and the ground state of the universe depends on the potential of the Higgs field that permeates the vacuum of the universe. So as you can see over here, you have two ground states. One is a false, a metastable ground state, a higher ground state, and one is a lower ground state, which means so so if the universe is in uh, let's say so there's a local minimum and a global minimum, and the local minimum, if it is more energetic than the global minimum, then the universe may be in a metastable uh, vacuum, in a local vacuum. So what do we mean by all this is what we have to understand. But you can see here, stable, metastable, all that. So if the universe lies in a global minimum, in the global minimum of the Higgs potential, which is the true vacuum state, then it is stable. But if the minimum of is local, and there is another minimum which is deeper than that, then the vacuum is false and the universe is metastable. So let us see here. This is an example with I think this is a better representation. Can I find a better image? Let us quickly look here. Maybe this. Okay, let's take this as the thing. Okay, so maybe we are at this point, which is metastable, but there could be a global minimum that is deeper and different. So if we are in a false vacuum, a metastable vacuum, then the universe is metastable, and what might happen is that our universe might tunnel out of where we are into the true vacuum state via a process called quantum tunneling. So in quantum theory, a stable or true vacuum corresponds to the global minimum of the scalar potential, which is the Higgs potential. And a metastable or false vacuum, it is instead a local minimum, not a global minimum. And if our universe lies in the only minimum of the Higgs potential, then we are fine. or if the universe lies in the deepest minimum of the Higgs potential, then we are fine. But if we lie in a local minimum and a deeper minimum exists, then the universe will eventually, via quantum tunneling, uh, tunnel into the other state, into the true vacuum. And if that happens, then everything that we know of will be destroyed. So, this process of quantum tunneling is unpredictable. Okay. Quantum tunneling is well known in quantum mechanics. Students study that. Uh, so quantum tunneling is unpredictable. It can happen completely spontaneously. And if the universe is in a false vacuum of the Higgs potential, of the Higgs field, it could potentially decay, tunnel to a lower energy state at any time. It could happen spontaneously. For example, we know there are quantum fluctuations in the universe. Quantum fluctuations could potentially cause a small region of space in the universe to tunnel through the energy barrier and transition to the true vacuum state of the Higgs potential, of the Higgs field. And this would create a bubble, a small bubble of true vacuum that would then expand outwards at the speed of light. So this decay would spread at the speed of light, creating a bubble, an ever expanding bubble at the speed of light of true vacuum that expands outward. So you're correct that we may not be able to detect this decay before it reaches us because it is traveling at the speed of light, and no information can travel faster than the speed of light. And this decay of a false vacuum would have catastrophic consequences for the universe as we know it. So as this bubble of true vacuum expands, it would fundamentally alter the laws of physics and all the properties of matter within it. So this would definitely lead to the end of all matter as we know it in the affected regions. Matter will, once this happens, matter will have very different properties than what we know. So that definitely means the end of all life if this reaches the earth. So that's what this is. And of course the probability of such a thing, such a catastrophic event happening is extremely small, because we know that the universe has remained in its present state for at least about 13.8 billion years. So, this concept of false vacuum is definitely well established in theoretical physics, but we have absolutely no experimental evidence that our universe is in a false vacuum state. But the even this the smallest probability, smallest possibility of such an end of the world that could happen, obviously is scary. It's disquieting, and if it happens, it's definitely going to be the end of the universe as we know it, and definitely the end of life as we know it. But I suppose we won't even notice if it happens. We won't have time to realize what's happening. It'll just happen in an instant. And a third question by Yajnavalka. Does the top quark decay before it gets affected by color confinement? And thus, can a bare top quark be observed? In general, can bare quarks be observed above the Hagedorn temperature? Okay, we have a number of concepts over here that we have to speak about. One is the Hagedorn temperature. So, what is this Hagedorn temperature? So the Hagedorn temperature is a theoretical temperature limit in particle physics in the context of what we call hadronic matter. What is hadronic matter? Hadronic matter is your standard matter that you are aware of, matter that is made of quarks. So protons and neutrons are made of quarks. Electrons aren't made of quarks. Okay, electrons aren't hadrons, they're leptons. But the universe that we know, the world that we know, is all hadronic matter. And the Hagedorn temperature is a theoretical temperature limit in the context of hadronic matter. So at this temperature, the Hagedorn temperature, if you add more energy to a system of particles, like let's say you have a particle accelerator, or you have the early universe, and you add more energy to a system of particles at this temperature, then this doesn't increase the temperature. It instead produces more particles. Okay. So the idea is that at very high temperatures, the energy density is so high that it continuously converts into the creation of new particles. So the Hagedorn temperature is a theoretical upper limit on the temperature of matter. beyond which our current understanding of particle physics breaks down. And this is essentially represents a phase transition between different phases of matter, like between water and ice or water and steam. These are different phases of water, right? Similarly, the Hagedorn temperature represents a phase transition temperature, and it's about 1.75 trillion Kelvin, 1.7 times 10 raised to 12 Kelvin. That's the Hagedorn temperature. That is what it is. Now we're talking about bare quarks, right? So at temperatures above the Hagedorn temperature, there will be a phase transition and there will be a different state of matter that will exist. And that phase of matter, state of matter, is called a quark gluon plasma. In a quark gluon plasma, quarks and gluons are deconfined and they can move freely. It's a soup of quarks and gluons. Gluons are force carriers, so to say. Okay, so they will all intermingle. They will be deconfined and they'll move around freely. It will be quark gluon soup, quark gluon plasma. And this state of matter could potentially allow for the observation of what you call bare quarks. Okay, now what is color confinement? That's another term that we are using over here, color confinement. So color confinement states that quarks cannot be isolated singularly. Quarks can only be found in bound states called hadrons. Okay, so there are 6 quarks: up, down, top, bottom, strange, charm, and these are the fundamental building blocks of the of hadronic matter. So confinement says that you cannot have isolated quarks. Quarks are always found in bound states called hadrons. Now there is something called color charge. Okay, and think of it as a quantum property. It's not really a charge, and it's not really colors like red, green, and blue. Even though quarks carry what we call one of the 3 color charges, red, green, and blue, but this color charge is actually a kind of quantum property. So quarks carry one of 3 color charges: red, green, blue, and anti-quarks carry anti-colors: anti-red, red, anti-green, anti-blue. And there is a property called color neutrality. So hadrons, bound states of quarks, are always color neutral. So this can be achieved by either combining 3 quarks with different colors into baryons. Okay, protons and neutrons are baryons and they are made of 3 quarks. Or you can combine a quark and an anti-quark with corresponding color and anti-color charge, which are mesons, pions, kaons, etc. Okay, so that's how you achieve color neutrality. So similar to how atoms are electrically neutral because they have equal numbers of protons and electrons, similarly hadrons are color neutral because their quark colors combine to cancel each other out. Now there is a strong force involved in quark interactions, and the strong force between quarks increases with distance. Okay, in electromagnetism, in the gravitational force, when objects or 2 bodies move away from each other, the force decreases with distance, right? With increasing distance, the force decreases 1 upon r. But in quarks, the strong force between quarks increases with difference. So imagine 2 quarks that are connected by a rubber band, a flux tube. So if you pull them apart, you're going to have to impart a tremendous amount of energy. And as you pull them apart, the tension in this band, this rubber band that connects the 2 quarks, increases until the band snaps. And when the band snaps, it creates 2 new ends, and this snapping essentially represents the creation of a new quark anti-quark pair. This leads to the formation of 2 new hadrons instead of isolating 2 single quarks. So that's essentially what it is. Okay, that is color confinement and all that. Now above the Hagedorn temperature, the concept of confinement, color confinement, no longer applies, and the thermal energy is sufficient to overcome the strong force. The thermal energy of the temperature is sufficient to overcome the strong force that confines quarks within hadrons. And that's how you have the formation of the quark gluon plasma, where quarks and gluons freely move around over large distances. And this state of matter is believed to have existed just after the Big Bang. Now you are mentioning the top quark. It is the heaviest of the quarks. It is an extremely massive quark. It's unique among all the quarks because it is tremendously massive. It decays extremely quickly, and it decays faster than the time it would take for color confinement, which is the process that binds quarks together to form hadrons. Okay, so top quarks are unique, such that in such a way that it is possible to observe an unconfined bare top quark in experiments. And that is about it. Okay, Rohan says the following is a quote from Brian Greene's book Until the End of Time. It's only by comparison that with the demonstrably incorrect classical view, the view we humans discovered first because it's both simpler and extraordinarily accurate on the scales accessible to human senses, that quantum reality seems hazy. It's actually the classical perspective that provides an approximate and hence imprecise view of the true quantum reality. What are my views on this? Are we classical beings living in a quantum world? Well, the world definitely emerges from the quantum domain, from the ultra microscopic scale, and all the processes, all the phenomena, whatever we see, uh, originates from quantum mechanics. I mean, if you see light is a quantum mechanical phenomenon. The very fact that matter occupies space comes from Pauli's exclusion principle, which is a quantum mechanical principle. Everything that we experience has a quantum mechanical origin for sure. So we inhabit a world that we perceive such that it doesn't have any quantum mechanical phenomena except for certain objects like crystals, etc., whose properties are entirely quantum mechanical. But most of the things that we experience are non-quantum phenomena, and these are what we call the classical phenomena. So the world we experience is a classical world, and quantum mechanics obviously is extremely complicated. It involves an extremely small scales which we can't perceive. um, so that obviously is the true world, but the world we observe is also the true world, and our brains, our minds aren't that powerful that we could perceive quantum phenomena and process them in real time, because that is so complicated. Now imagine you have got a phone. Okay, you got a phone here, and you see stuff on the screen, and if you but inside the phone you have voltages, and you have gates, and you have all kinds of circuits, and you've got billions and billions of uh, millions, maybe billions of circuits on the silicon wafer. And if you want to send an email, you have to toggle all kinds of voltages and do whatnot. You think you can do it cognitively in real time? You can't. So what the phone interface shows you is a very very high level abstraction of the complexity that happens inside. And that's kind of how we see the world, because our brains aren't that complicated. So the classical world is obviously the true world, but the quantum world is also the true world. So these are different representations of the world. this these are different ways in which we can think of the world, interpret the world, and that's just what it is. So we are classical beings, but we emerge uh, from the quantum scale. Our thoughts, I don't know where they emerge from. Our consciousness, I don't know where that comes from. We still don't know. But yeah, but I wouldn't say that the classical view is incorrect. Uh, it is correct to a certain um, degree of correctness. It depends up to which decimal point you want it to be correct. That's just how it is. Aditya S1 says, recently you tweeted about encouraging learning physics all over again from scratch. So I need advice on that. Please suggest how to approach physics from scratch, as I'm already in my undergraduate level now. Oh, so I remember a few days ago somebody had said that he or she wants to relearn physics a priori from scratch. And I kind of just encourage that person, yeah, that I approve of it. But how would one do that? So look, I was talking about learning physics from scratch all over again, like learning for the sake of actually learning, with the objective of maybe doing actual research in physics. If you are in the at the undergraduate level, then you need to get your degrees and all that, which means you have to pass exams. So learning physics for the purpose of passing exams is extremely different from learning physics for the sake of doing research in physics. Very, very different approaches are required. When it comes to passing exams, you have to be very ruthless, very practical. You do take shortcuts. Shortcuts are your best friend. You have to memorize lots of equations and formula, just mug it up, and you got to solve lots of problems. And in the Indian context, you have to learn how to write like 50-page essays for some mundane topic, and 10 such essays you have to write in one exam in a matter of 3 hours. So it depends on which exam, which academic system, and so on. So my I am not great at giving advice about how to learn physics for the purpose of passing exams. That's never something that has interested me. I can give you advice about how to genuinely learn physics a priori from scratch if you want to do research in physics in whatever field interests you. So I would say, if you want to go back to the basics and learn physics from scratch, and at the end of the process you want to be able to do actual research at the highest level, it would take you 5 years, roughly, give or take. And if I were to do that, I would spend at least 2 years just doing basic math. Go back to your high school or college level mathematics, do relearn algebra. Yeah, why not relearn algebra? Do all the Shom series books, just chew them up, do all the problems, relearn calculus, differential equations, um, uh, what else do we have in quantum mechanics? Linear algebra, matrices, all of that. Learn all of that, then go through the books of mathematical methods for physics at two different levels. One would be Mary Bose, the other would be uh, what is that? I have the book behind me. So there's at least two books you need to do. And then once you're done with all of that and you're really, really solid with math, because when you start solving problems in the mathematical methods for physics books, uh, then you're already doing physics. Even if you take a proper course or thick textbook on differential equations, you're doing physics right there, whether you know it or not. So once you're done with the mathematics, you solved all the problems, then you spend 1 year at least doing your classical physics, which is Newtonian mechanics, maybe uh, definitely Newtonian mechanics, electromagnetism, and statistical physics, statistical mechanics, all that. Then you move on to quantum mechanics and relativity, and then you would spend some time solving hundreds of problems in quantum mechanics. You start with Griffiths, then you go to Zethili, and then you go to Shankar's level, and eventually land on Lifshitz. Uh, and then you obviously have to learn tensor calculus, and you have to do at least a couple of books on relativity. It's a long climb ahead. But if you go through this entire process, which might take you 5 years, you're going to be solidly equipped for doing actual research in physics. That's how I would do it. If you're in your undergraduate level and you have to pass exams, I would not advocate this approach. Take your shortcuts, do your memorization, you're mugging up, solve as many problems as possible. Ideally, just take the past 10 years exam papers and solve them over and over again. That's what you would do. That's how you would do very well in your exams. You'll get your degree, but I'm not sure how well you will learn physics by doing this. So my point is, in life you have to be practical. You cannot be idealistic. If you're a student, you have to get your goddamn degree. You got to get good marks. So be practical, be ruthless, do what's required. Then you can see. Then if you want, you can learn actual physics, and you can follow the guidelines, the outline I just laid out for that, which may take you 5 years. But physics is a extremely vast field, and there's so much to learn in that. It takes time, and the entire basis of physics is mathematics. You have to be good at mathematics. At least you need to be good at learning math. Okay, there's a problem I need to solve. How do I solve it? Oh yeah, I need this piece of math. So let me learn it in the next 2-3 days. So you should be able to quickly learn new math if required. Maybe you need to learn group theory, maybe Galois groups or whatever. I mean, Einstein had to learn tensors just so that he could formulate the equations of general relativity. And he hated math. He was not good at math. Heisenberg did not know what a commutator was. Okay, when he ran into his uncertainty principle on an island called Helgoland. So he didn't know what commutators were. He did not know what matrices were when he formulated matrix mechanics. and so on. So you, as a theoretical physicist, you have to be able to quickly pick up new math, and that's a skill you need to have. All right, I am done with all the questions from the comments. Let's take some questions from the live chat. Manasi says, mug up physics. No, you don't mug up physics. You mug up the formulas and the equations and all the shortcuts for passing exams. But if you want to do real research, you don't mug up anything. You need to understand the concepts. And you have all the textbooks. So you need to just open the textbook and find whatever you need to find. For example, I was talking about a gas of photons. What are the properties of a gas of photons? What is the equation of state for a gas of photons? What is the representation of the temperature and the pressure of a gas of photons? What's the entropy of a gas of photons, and so on and so forth? I don't need to memorize that. I would never do that. I'll just open Landau and Lifshitz, wherever it is, the book on statistical mechanics, I think, or whichever one it is. I got a whole bunch of them. You find the thing and then you take that and use it. So in the real world, you don't need to mug up stuff. But for exams in India, especially in this stupid, idiotic Indian academic system, you don't mug up stuff, which is unfortunate. Unfortunate. We're going to take questions about physics and science today, not about mysticism and religion and history, astrology, all that. All right? Please ask me questions about science today. Tomorrow, I will take questions about everything else. Okay. Okay, let's take this. Arkhamanna says, after JWST, James Webb Space Telescope, discovered galaxies which are expected to be older than the. Excuse me. What? Excuse me? Okay, let me read the question. After the James Webb Space Telescope discovered galaxies which are expected to be older than the Big Bang, should we now consider that we have to revise the Big Bang theory once again? Okay, let me explain what's happened. The James Webb Space Telescope has discovered the oldest galaxies that we have discovered thus far. And they are, I assure you, they're not older than the Big Bang, but they're older than what we expected the first galaxies to be. They're about 200 million years. The first galaxies emerged about 200 or so million years after the Big Bang. We expect that the first galaxies would emerge about a billion or so years after the Big Bang. So they are way too early. They formed way too early. So that kind of forces us now to revise our understanding of how galaxies form. So that's what happened. That's what's happened. We don't have to revise the Big Bang theory. These galaxies aren't older than the Big Bang. Nothing at all is older than the Big Bang. That is simply an impossibility. Okay? So we have discovered the oldest galaxies ever, and we kind of don't know how come they are so old. I mean, so old. Yes. How did they form so quickly after the Big Bang? 200 or 230 or so million years after the Big Bang, which is ridiculous, which is incredible. So that is the problem we're facing. It's a good problem to have. We always want to, as a physicist, you want to discover new things which kind of upset everything, upset and go against the current understanding of physics, because that's where there's a new problem to solve. And physics is all about solving new problems. So you find new data which represents a problem, a crisis, and you say, great, now I have something to do. Otherwise, it's all business as usual. So that's what's happened. I'm glad this has happened. The JWST is throwing up new data, which is kind of revising the way we look at the universe, and that's what's happened. So we don't have the answers yet, but I'm sure we will figure it out sooner or later. Mansi is saying, I'm saying for the exams, it's a royal subject, a subject of understanding. Of course, for the exams, yes, you have to mug up physics for the exams. I completely agree. And that's what I also say. You have to be practical, and you should mug up physics for the exams if you have to. And once again, Mansi says, what are the current challenges in physics? There are so many things that are not understood in physics. For example, all the stuff that the James Webb Space Telescope is throwing up. I mean, that is challenging our current understanding of physics. How do black holes form? How do supermassive black holes form? And that's not related to JWST, but overall, we don't know how supermassive black holes form. They should take a very long time to form, but even every galaxy seems to have one at the center. How does that happen? What's dark matter? We don't know what dark matter is. What is dark energy? We don't have the, the, the least clue as to what dark energy is. So 95% of the universe is dark. Now, then what are neutrino oscillations? Where do they come from? Um, there's so much more. Why do we have various constants? Constant quantities in physics. Why do they have those quantities? Why do they have those specific values? Various constants uh, like the gravitational constant, like the gravitational coupling constant, the electromagnetic magnetic coupling constant, various constants in physics which seem to have completely arbitrary values. Why do these values exist? Why not other values? uh, so much more, right? Why is the universe expanding? Why is the expansion accelerating? What's the ultimate fate of the universe? We're going to have a big rip, or we're going to have a big crunch. What is the true nature of gravity? We don't understand gravity at all. We simply don't understand gravity. What is time? My goodness. What is time? Where does it come from? Is it an emergent property of the universe? Do we have atoms and molecules of time? Or is it something that comes from outside the universe? I mean, in quantum mechanics, time is an external parameter. It's a classical parameter. It's not a quantum parameter. It doesn't emerge out of quantum mechanics. It comes into quantum mechanics from outside. So many open problems in physics. We understand next to nothing of the universe. Okay, so there's challenges everywhere, absolutely everywhere. What is consciousness? I mean, it should have a physical explanation, should it not? Are we living in a simulation? So much. I mean, that's why physics is so fascinating, because there are so many open problems in physics. Okay, let's take questions from other people. uh, Karan Nalawat says, what is ether? So ether there's no ether. Okay, there's no such thing as ether. But there used to be this belief in the past, until I think the late 19th century, maybe even the early 20th century, that there is something called the ether, which permeates space. And because we know that space is a vacuum, then how does light propagate in space? I mean, waves need a medium to propagate, right? How can waves propagate without a medium? Waves need a medium within which to propagate. So that's why there has to be an ether out there, something called the ether, within which light propagates. That was the belief. And then there was a very famous experiment called the Michelson-Morley experiment, with the Michelson-Morley interferometer, which is the basis for LIGO, which is the gravitational wave observators that we have. So the Michelson-Morley experiment conclusively proved that ether doesn't exist. Okay, so that is now an obsolete concept, and we know that ether doesn't exist. But it was this hypothetical uh, medium through which light could propagate. Now we know that light doesn't need a medium to propagate. Okay. Um, Ishant Singh says, is everything predestined according to science? Super determinism, isn't it? So, look, we know that the laws of physics seem to be deterministic. If you have a ball and you drop it, it's going to follow the laws of physics. So you have an initial set of initial conditions. The ball is at a certain altitude, certain height above the ground, and I drop it, I let it go. It has a certain mass. It's going to fall towards the ground. It's going to bounce off it, and you can, based on very simple equations, you can predict the entire path of the ball all the way into the future. And if you can do that into the future, you can even do it into the past if you know all the parameters of the system. That system includes me, the atmosphere, the environment, the temperature, the motion of the Earth, the motion of the sun, the motion of the sun around the Milky Way, the motion of the Milky Way around the local supercluster, and so on and so forth. All the parameters, if you know, then you can actually essentially predict the future as well as the past. So, and it's all differential equations. So from that perspective, it looks like everything is predetermined, predestined. And then you have uncertainty, because quantum mechanics is not deterministic, it is probabilistic. So you have quantum fluctuations which are entirely random, and you have the uncertainties in quantum mechanics, the Heisenberg uncertainty principle. So those that introduces randomness in the universe, through because of which you can't predict everything. But that randomness is also entirely random, and so it's so the question actually is, the real question over here is, do we have free will? If I'm choosing to snap my fingers here, right here, is it because I have decided to do it, or is it because it was just programmed into the initial conditions of the universe, that at this point in time this being over here will snap his fingers? That's a real question, and we don't quite have the answers to that, or maybe we do. And it is kind of scary, because if you look deep into this, it may actually end up telling you that we don't have free will and everything is predetermined, predestined. But that's not how I see it. At least I choose not to see it that way. I want to believe that I have free will. All right. Okay. Mm, Movies says, is 2 plus 2 equals 4? Well, as far as I know, it is 2 plus 2 equals 4. Now let's take some other question. So many questions. Let me try and take questions from someone has not asked a question thus far. I will not take questions about history, etc., etc. Okay, Shri Vatsa says, if space itself can expand faster than the speed of light, then why are gravitational waves limited to travel at the speed of light? So, gravitational waves propagate within the fabric of space time. And space time itself expands due to mysterious processes, and it can expand faster than the speed of light. And if you have a gravitational wave that's propagating within space-time while it is expanding, the gravitational wave will only expand, will only travel at the speed of light. That's just how it is. So yeah, you can, there is a universal speed limit in the universe, which is the speed of light, but that applies to objects and processes and phenomena that travel within space-time and occur within the fabric of space-time. But the fabric of space-time itself can expand at any speed. It's like having a balloon. You expand a balloon, there's an ant sitting on the balloon, okay, on the surface of the balloon. When you expand it hard, and the balloon expands whoosh like that, then the ant may end up traveling from its perspective faster than the speed of light, but it's actually not traveling. It is space-time itself which is expanding. So that's how it is. I know it's counterintuitive, but that's just the way it is. There is so much about relativity and quantum mechanics that is not intuitive at all. It simply doesn't fit in with the way we have always experienced the world, because we live on a planet which is traveling around the sun, and in the environment that we live in, these phenomena don't happen. Relativistic phenomena, we don't experience them ever. Such phenomena, you will experience them if you go near a black hole, or yeah, where you have extremes of energy density or mass density or extreme velocities. That's where you can observe relativistic effects, and we are not in such an environment. So it is completely counterintuitive to whatever we imagine, but that's just the way it is. I will not take questions about tantra mantra, okay, in today's session at least. uh why do people ask questions about other topics when this is a science episode? um Some questions I've taken many times, but okay, let's see. Udit Narayan says, is there a center of the universe? Yes, from my perspective, the center of the universe is right here. From your perspective, the center of the universe is where you are. It's because uh, the observable universe is something that is centered around you. That's because, look, the observable universe has a radius of about, has a diameter of about 95 billion light years. Okay, because of the expansion of the universe. And the center of the observable universe is where you are, or where I am. From my perspective, it's where I am. From the your perspective, it's where you are. And from our collective perspective, it's the planet Earth, because it's from here that we are looking around. So it's the center of the observable universe. But the true center of the universe, we don't know where it is. We don't know how large the universe is, whether it is infinite, whether it is finite, what shape it has, we have no idea. But we only can see a certain portion of the universe. And from that perspective, the center is where we are. Um, Ojas says, there are so many Earth like planets in their respective Goldilocks zones. Could they also have humans? The scariest thing to find in outer space would be non-Earthian humans. Well, we know of multiple planets by now that exist in their respective Goldilocks zones of their parent stars. The Goldilocks zone is that specific region around a star where the temperature is such that you can have liquid water. So for our star system, the sun, the Goldilocks zone, in the Goldilocks zone, we have three planets: Venus, Earth, and Mars. And depending on the size of the sun and the temperature of the star and all that, you can have different sizes and distances of the Goldilocks zone. And we know of many planets, exoplanets, that exist in their respective Goldilocks zones. So could they also have humans? Look, it's possible that there could be life there. It's also possible that there could be intelligent life there. Could there be human-like life there? That's also possible. Okay, but we haven't observed that. We have never seen it thus far. The possibility is there. I mean, there are 10 raised to see. There is at least 10 raised to 22 or 23 planets in the observable universe. There is one with 22 zeros after it, and it's just a probabilistic likely. I mean, it's almost a certainty that life and intelligent life would exist somewhere out there. But the universe is so large that we may never be able to discover it. Or maybe if you're lucky, or maybe if you're unlucky, you might discover it. So I I think it's possible that there could be life, intelligent life, maybe even human-like life over there. And yeah, it would be scary perhaps to find such life, to discover such life and come across that. Okay. Um, what is escape velocity? So the escape velocity for any object is that velocity which will allow your rocket, your spacecraft, to break free of the gravitational pull of that object. So for the Earth, I believe the escape velocity is what, 11, 12 or something kilometers per second. For the moon, it's much lesser than that of the Earth. So there is a formula for escape velocity which you can derive using basic Newtonian mechanics, which you can look up, and it's the minimum velocity that your spacecraft or your projectile needs to permanently escape the gravitational potential of the planet or the star that it wants to escape from. That is escape velocity. For the Earth, I think it's around 11 or 12 kilometers per second. For the sun, for the solar system, it may be way more, maybe hundreds of kilometers per second. Okay, do we have anything else? There's obviously lots of other questions. And Uma Maheshwari says, according to quantum mechanics, is it true that when there is no observer, there is no observation? Then if we are not being observed, then do we theoretically not exist? Well, it's a good question, right? Imagine we all do a thought experiment, we humans. We decide that at so and so time tomorrow, none of us will look at the moon. Okay, so everybody on the planet Earth will not look at the moon. We'll all look somewhere else. Will the moon disappear then? So this is a kind of a philosophical thought experiment. The observer effect doesn't mean that actually. The observer effect means that the act of observing something ends up modifying or changing the thing that you're observing. That's what it means. I gave a proper answer just at the beginning of this episode. You can, once the episode is over, you can go and check it out again. So it doesn't mean that. Okay, so because you're not observing or nobody's observing something, it doesn't mean it doesn't exist. It does exist, but so the observer effect doesn't mean that the act of observation makes something exist. It means that the act of observation changes that thing that you're observing or measuring. Okay, so yeah, I mean, you can think of it that way. That um, for something to exist, it has to be observed in that way, and you could then argue that if we exist, then if somebody from outside has to observe something for it to exist, then who is observing our universe? Yeah. Okay, I think I will now essentially take maybe one more question. I've taken Dyson spheres lots of times. I have many clips on this channel about Dyson sphere. Om Sood says that the Higgs boson was discovered on today's date. Yes, yes. Happy birthday, Higgs boson. And that's about it. Um, Kishan Borkar says, no, it's not a stupid question. If there's an object to the left and to the right of a black hole, is it possible that some of the light is absorbed by the black hole and we see the fusion of two objects as one? You will see very strange effects. You can see the backside of a black hole at the front. Yes. So you will have the warping of light around a black hole. Okay, and you may see objects get stretched out, apparently stretched out, and you could see two objects get combined because of the way light travels in curved paths around a black hole. It's not a stupid question, it's actually a very good question. So yes, you could see two objects appear to merge together because of gravitational lensing. Yeah, so it will certainly happen. You will have these distortions of light, and because of light traveling in curved paths around black holes. Okay, I'm gonna end it over here today. I apologize to everybody else whose questions I could not take, but there are so many other questions. But I'm gonna end it over here, and I'm gonna keep doing these sessions, and I'll take as many as possible going forward in the future on an ongoing basis. So thank you so much for all your questions. Thank you so much for watching, for participating, and I will see you very soon in the next live stream. Please keep learning. Please keep asking questions, and please keep raising your standards. Thank you so much. See you very soon.